Processing millions of transactions across shifting currency boundaries creates a persistent pressure on database integrity. At this scale, even a minor synchronization error between a product rule and a balance state results in untraceable data drift. To prevent this, modern financial architecture requires a clean separation of concerns. You have the orchestration engine, which manages the complexity of KYC, product limits, and business rules, and you have the operational ledger. The operational ledger doesn't calculate interest or verify identities. It functions as a deterministic register, recording only the immutable history of fund movements. To maintain accurate balances, it must enforce double entry invariance, isolate cross-currency risk, and manage high-frequency write contention. Physically decoupling these systems ensures the ledger remains isolated from the frequent updates and logic changes in the product layer. It creates a stable system of record that remains consistent even as the front end evolves. The foundational data model for this operational ledger is built on three primary tables: account, transaction, and entry. The Postgres schema illustrates a critical rule. Monetary values are stored as integers, not decimals, preventing rounding errors. Within this structure, we enforce the double entry invariant. A transaction splits into two balanced entries, a debit and a credit. Their sum must absolutely equal 0, or the database rejects it. To preserve the audit trail, the ledger is append only. Existing records are never modified or deleted. Corrections are handled exclusively by posting new entries that offset the original error. Enforcing this zero-sum invariant at the database schema level ensures that integrity is preserved at the storage layer, protecting the data regardless of any errors in the application code above it. This structural integrity is challenged when a transaction crosses currency boundaries, for example, converting US dollars into euros. If we attempt to debit USD and credit euro in the same journal entry, the different currency denominations prevent the integers from offsetting. The transaction fails because it cannot sum to 0. The solution is currency position accounting. The transaction splits into 4 legs. In the base ledger, we debit the USD source and credit a USD counterposition, balancing the USD side to 0. Simultaneously, in the foreign ledger, we debit a euro position and credit the euro destination, balancing the euro side independently. The counterposition account in the base ledger records the historical cost basis of the transaction at the time it occurred. The foreign position account tracks the actual currency exposure the institution is now holding. This 4-leg method preserves the zero-sum invariant by ensuring each currency balances independently within its own ledger space. This architecture provides clear traceability. It isolates the financial risk of holding foreign currencies and prevents structural balance drift across the entire system. Because exchange rates fluctuate, the historical cost recorded in the counterposition account will eventually deviate from the current market value of those foreign assets. This divergence is resolved through period-end revaluation. Banks use this process to adjust the book value of foreign currency positions to reflect current market rates. The process compares the foreign currency balance, valued at the current spot rate, against the reporting currency balance held in the counterposition account. The system then generates an adjusting journal entry to account for the mathematical difference. This adjustment is recorded in a dedicated unrealized gain or loss account, bringing the recording currency books in line with economic reality. Automating this revaluation ensures compliance with accounting standards like IFRS 9, without ever needing to mutate the original historical entries in the ledger. Even a normalized append-only schema faces performance limits. High-frequency transactions targeting a single hotspot, such as a central treasury pool, create significant write contention. Standard pessimistic locking, which locks a database row before reading it, causes transactions to queue up. Under heavy load, this leads to increased latency and deadlocks. To maintain throughput, we use optimistic concurrency control. OCC defers synchronization to the final commit. First, the read phase fetches the balance without locking the database. Next, the validate phase calculates new balances in application memory. Finally, delight phase attempts a conditional update, committing only if the database lock version still matches the initial read. If another process updated the account in the meantime, the version check fails. The system rolls back the partial update and triggers an automated retry cycle with a randomized backoff delay. This approach trades database lock contention for application-level retry logic, allowing the system to handle a much higher volume of concurrent transactions. However, even OCC has limits. In extreme cases where hundreds of processes compete for the same row, the frequency of collisions can lead to a retry storm that degrades performance. We mitigate this through balance sharding. Here, a single logical account is split into multiple physical subbalance rows within the database. Incoming transactions are distributed across these subbalances, randomly selecting and locking only one of these rows, rather than hitting a single bottleneck. This effectively divides the lock contention by the number of shards, preserving transaction isolation while significantly increasing the write capacity. Balance sharding allows the ledger to scale to meet real-world transaction velocities without sacrificing the mathematical rigor of the double-entry model. By combining integer-based schemas, position accounting, and optimized concurrency, we build a ledger capable of managing complex global financial flows. To ensure this data remains trustworthy in a distributed environment, we add a final layer of cryptographic security. Modern ledgers generate a cryptographic hash for every entry, concatenated with the previous one to create an unbroken chain of data lineage. Any attempt to modify a historical record immediately breaks this hash chain, instantly alerting the system to the tampering. A multi-currency ledger is much more than just a table of balances. It is an essential, high-performance operational infrastructure. Adhering to these core engineering principles is the only way to ensure that a global financial system remains auditable, scalable, and perfectly accurate.